Hello everyone. The title of this video is Finding Laplace Transforms Using the Definition of a Laplace Transform. Now a Laplace transform of a function is a special kind of integral transform, and it's going to be very useful to us when we're solving certain kinds of initial value problems, in differential equations. Alright, so let's just get into something. I got three examples here, three pretty basic examples, but they demonstrate the definition use. Alright, so in all the examples in my video here, I have used the definition of Laplace transforms to find, and then this is the symbolism used for Laplace transforms. It's the script L, and then embraces the function that you're taking the transform of. So the Laplace transform of f of t, some function of t. For my first example, I'm going to be doing it with a piecewise defined function, where f of t is defined to be -1 when the values of t are from 0 to 1, including 0, not including 1, and f of t equals +1 for values of t greater than or equal to 1. Alright, so first, let's get into this. What is the definition of a Laplace transform? So for a function f of t defined for all positive values of t, the Laplace transform of f of t is an improper integral. Right? The integral from 0 to infinity of e to the negative st, that's the variable s introduced here, times the function f of t, and you're integrating with respect to t. Now hopefully you recall from maybe Calc 2 how to perform improper integration of this type where one of the limits is infinite. Additionally, from maybe Calc 3 multivariable, now we have this expression that's dependent on both these variables s and t, but we're integrating with respect to t, meaning that the final function here, what this integral transforms f of t into, is going to be a function capital F that depends only on s. Right. Okay. So again, if the function we're taking the Laplace transform is named little f of t, the function that is the Laplace that transforms into capital F is going to be a function of only s. All right. And we also are going to have to pay attention to what values of s would actually make this limit, this integral exist. And I'll point that out as we go through the examples. What values do s need to take on in order for the limit to this integral, the limit, to exist. Okay, so again here, piecewise defined function. The Laplace transform of this function, now again it has two different definitions here, so I'm just going to write f of t is again the integral from 0 to infinity of e to the negative st times f of t dt. And since this function is defined differently on different intervals, what I'm going to do is I'm going to break this up into those intervals and add those integrals. So the integral from 0 to infinity I can break up to the integral from 0 to 1, right? Because that first piece of the function is defined that way on the interval from 0 to 1 of e to the negative st times, and then f of t on this interval is defined as simply -1, and then you have dt plus, and then the rest of it, the integral from 1 to infinity We went from 0 to 1, then 1 to infinity, giving me 0 to infinity of e to the negative st times f of t. But f of t, defined on this interval, right, when t is greater than or equal to 1, is defined as just 1 dt. And don't forget how to do these limits, these improper integrals where one of the limits is infinite. I'm going to change this into a limit. And you could use any variable you wish other than s and t. Let me show you what I'm going to do. All right. So first off, this integral is pretty easy to take. This would just be just 1 over s times e to the negative st. Remember, you're integrating with respect to t. So s is treated as a constant. And then this is evaluated from 0 to 1. Now that's from t equals 0. Remember, this is with respect to t. From t equals 0 to t equals 1. Okay, and then plus, and as I said earlier, we're going to think of this as a limit. Now I could use, I'll use the letter b here. The limit as b approaches infinity of the integral from 1 to b of e to the negative st dt. Alright, so this first part, pretty simple. This should just be 1 over s times e to the negative s. Then, that's when t equals 1. Then minus when t equals 0, that'd just be minus 1 over s times e to the 0. So just minus 1 over s. Plus the limit as b approaches infinity of, and here, again, pretty simple antiderivative, be negative 1 over s e to the negative st, evaluated from t equals 1 to t equals b, right? And then we're going to have b approach infinity. So I've got the following: 1 over s times e to the negative s minus 1 over s plus the limit as b approaches infinity of the following: negative 1 over s times e to the negative s times b, then minus negative 1 over s times e to the negative s times 1. So plus 1 over s times e to the negative s times 1, or just negative s. Now you got to be careful here. Off to the side, this limit doesn't exist for all values of s. If s were positive, right? If s were positive and b was approaching infinity, that would be good, right? Because if s were positive and you got the opposite of that, this would be a negative power here, and e to a higher and higher negative power would be approaching 0. Now if s were negative, that would be bad, right? Because if s were negative, the opposite of that would be positive. This would be some bigger positive number. E to some bigger and bigger positive number would just go to infinity. So off to the side here, I'm going to say, let's assume then, in order for this limit to actually exist, assume that s is a positive number. And I'll mention that in every single one of these Laplace transform limits, what the value of s needs to be in order for the limits to exist. So if that's the case, if s is positive, this is approaching 0 then, right, as b approaches infinity. And so what I'm left with is 1 over s times e to the negative s minus 1 over s plus, and then this limit is just simply 1 over s times e to the negative s, right? This expression here didn't have b in it at all, so it stays constant. Then I got some like terms, these terms with the e to the negative s involved. So that'd be what? 2 over s. I got 2 of them. 2 over s times e to the negative s, and then minus 1 over s. And there we go. And this is what we're going to call, capital F. If the original function, the function we were transforming, was little f of t, this will be called, capital F of s. You see how it is a function of only the variable s now. Okay. Great. Again, s being greater than 0, of course, too. All right, so that's just one example. Now that example there, had a piecewise defined function. So if you're ever given a piecewise defined function, just make sure to break up your integral to those pieces, to those intervals. All right, so I'm going to do this again a couple more times with some pretty basic functions, I feel. So here's another one. We're asked to use the definition of Laplace transforms to find the Laplace transform of f of t, where here f of t is e to the t plus 7. Right, so what's the Laplace transform of e to the t plus 7? So again, same definition, integral from 0 to infinity of e to the negative st times the function times e to the t plus 7 power. And then with respect to t, right, dt. All right, so as I did before, as you should be doing with these improper integrals like of this form, I'm writing this as a limit. All right, so this is the limit, and again I'll use the letter b as b approaches infinity of the integral from 0 to b. Now if I rate this, these both have base e, and in fact there's a constant I can pull out of this. That'd be e to the 7th. And then I have e to the negative st plus t. That'd be negative s plus 1 times t, or 1 minus s times t power, using some properties of exponents here, and then dt. And as I said before, this is a constant. I can pull that constant out. We have e to the 7th pulled out, times, and then I guess I should write the limit as b approaches infinity of, and then when I pull e to the 7th out, this is a pretty easy integral, right? It's 1 over negative s plus 1 times e to the negative s plus 1, or 1 minus s, whatever you want to write, t. And we're evaluating this from t equals 0 to t equals b, right? And then letting b approach infinity. All right, so this is e to the 7th times, again I gotta write this, the limit as b approaches infinity. All right, sorry about that. Of the following. Now if I put in b, we'd have e to the negative s plus 1 times b divided by negative s plus 1. And then I put in 0 and subtract, so minus just 1 over negative s plus 1. Right. Okay, now again I got to think, after evaluating the integral, I have to think of the values of s that would enable this to actually have a limit, if there are such values of s. So again, if negative s plus 1, if this negative s plus 1 were positive, that would be bad, because then that'd be positive, b's getting big, positive, this would approach infinity, it would blow up, the limit wouldn't exist. So I would need negative s plus 1 to be negative, right? In other words, I need s to be greater than 1, right? I need the value of s to be greater than 1, and if that were the case, then this limit would approach 0, right? Because this would be e to some bigger and bigger negative power approaching 0 then. So when all's said and done, after taking this limit, I have e to the 7th divided by, and then I'll put the negative down here. The opposite of negative s plus 1 is s minus 1. And there we go. There's our function of s, capital F of s, the Laplace transform of e to the t plus 7th power. Would be e to the 7th divided by, s minus 1. And that's as simple as that's going to get. Okay, but yeah, same setup, same integral. That's just, the integration. Now, so far, the antiderivatives I've had to take, the integrals I've had to take haven't been too terribly difficult. So I just wanted to do one more example where maybe we'll have to bring in some other method of integration, like integration by parts, to help us out. All right, so I've got one final example of finding the Laplace transform of a function. And here's a function that's a combination of a polynomial. It's a product of a polynomial in t and an exponential. So again, the Laplace transform of t times e to the 4t is yet again, set it up, the integral from 0 to infinity of e to the negative st times the function times t e to the 4t, and then with respect to t. And again, this should end up being a function of s only. Okay, so I'm going to write this stuff out in a little different way. As a limit, this is the limit as b, again I'll use b, as b approaches infinity, of the integral from 0 to b of, and I'll put the t first, t times, and then combine the e's with some properties of exponents at e to the negative s plus 4 times t power, right? And then again dt. Alright, so my integrand here, right, is a product of, again, a polynomial and an exponential function. So when you have that kind of stuff going on, right, when you have a product of two different classes of functions as your integrand, integration by parts, right, we'll do by parts over here. I'll write up the little parts formula, refresh your memory. Remember the integral of u times dv was equal to u times v minus the integral of v times du, right, where we have to assign u and v, or u and dv. So in this example, I think a nice choice would be have u be the t, and then dv is the rest of it with the differential, right? E to the negative s plus 4 times t dt. And then differentiating the u, we have du would simply be dt. Integrating this, v equals 1 over negative s plus 4, or 4 minus s, whichever one you want to write, times e to the negative s plus 4 times t. Alright, so what we're getting here is then the following of the limit as b approaches infinity of, now u times v would be t over negative s plus 4 times e to the negative s plus 4 times t, right? And evaluating this from 0 to b, right, that's u times v. And then minus the integral of v du. I could pull the constant out, 1 over negative s plus 4, and then we're doing the integral from 0 to b of just e to the negative s plus 4t dt. All right, so all that in brackets there. Okay, so again, another pretty, now after I've done the parts here, integration by parts, we have an integral that's pretty easy to take here. All right. So let's do that. So now I have the limit as b approaches infinity of, now the first part here, I put in b for t, we'd have b times e to the negative s plus 4 times b divided by negative s plus 4. And then when I put in 0 for t, I get 0. So that's this first part. Then over here we have minus, now if I integrate this, this will be 1 over then negative s plus 4 squared. Right? You have 2 of those down in the denominator. Then times e to the negative s plus 4 times t, and this is evaluated from 0 to b. So I'll write this out further. Limit as b approaches infinity. If I have, again, this b times e to the negative s plus 4 times b over negative s plus 4, then minus 0 I'm not going to write. And then this stuff, you have minus 1 over, now I hope you see this, if I pull a negative out of this, it's being squared. So if I pull a negative 1 out of this, that'd be squared and make a positive 1, and then I'd have s minus 4 left over. So I'm going to make this s minus 4 squared instead of negative s plus 4 squared. Hopefully you see that, how I did that. Then times, and then this evaluated b in at 0. So e to the negative s plus 4 times b minus 1. I put in t 0 minus 1. Okay. And then just as before, in the previous couple of examples, we need to assume some things about the value of s in order for the limits to actually exist here. So again, if negative s plus 4 were positive, that would be awful, because b is approaching infinity. If negative s plus 4 were positive, this exponent would be blowing up and this whole expression would be blowing up. The limit wouldn't exist. So we need negative s plus 4 to be negative, to be less than 0. In other words, we need to assume here that s is greater than 4. All right, if s were greater than 4, then you'd have e to some big negative power, e to some big negative power. This term would be going to 0. This would be going to 0. All right, if s were greater than 4. And what I'm left with is this negative 1 over s minus 4 squared times 0 minus 1 times negative 1. This is positive 1 over the quantity s minus 4 squared. And there's the capital F of s. This is our Laplace transform for t times e to the 4t. All right. Wonderful. All right, so that's just a few examples there. Again, you're using the same expression in the beginning, the integral from 0 to infinity of e to the negative st times your function. And if it's piecewise, you're going to have to, like the first example was, you'd have to break up the integral as the sum of 2 integrals or 3 integrals, depending on how many pieces the function had. And then you're evaluating a limit, right? Now, the integration techniques that get used, substitutions, integration by parts, trig substitutions, maybe using some trig identities at some point, all that stuff. Hopefully you just remember how to do some integrals, from Calc 2, Calc 3, Calc 1. All right, and hopefully watching me go over these few examples help you out when you're working on problems similar to this, right? Asked to find the Laplace transform of a function using the definition. I think my next video is we're going to use some basic Laplace formulas that I would recommend you memorize to find the Laplace transforms of certain functions. Okay? And hopefully this helps you. Thank you very much for watching.